Okay, thank you very much for introducing me. Yes, in this afternoon, I'm going to talk about the self-sustaining process, the water scale, in the children's control. And my name is Hwang. I'm working with the campus between in Paris. Okay, the largest scale streaky motions in the children's flow have been found in recent numerical and experimental studies. These two figures are actually flow visualization for the boundary layer and pipe flow. As you can clearly see, there is long streaky movement where so sometimes they are meandering. And then one of the features of this structure is their spacing are scaled in the R2 unit, and also they carry a significant amount of the turbulent kinetic energy. So the formation of this kind of long streaky motion was initially suggested by the Kim and Adrian. And then here, you see the typical feature of the turbulent boundary layer. Here, there is a large scale motions, and then these large scale motions often thought to be, formed by the hairpin merger, growth and mergers, and then this broadcast packet again aligned coherently. So coherent alignment actually formed this uniform momentum distribution. This was one possible idea, and another idea was actually came out recently, and then it was actually conjectured by the several papers. And then this large-scale streaky motion self-sustained with a similar process to the Buckle-layer cycle. So this is a typical Buckle-layer cycle, and you have streamwise vortices, and then they are transformed to straight by Richter effect, and then you have the straight breakdown via secondary instability or transient growth or whatever. And then in the same analogy, it's conjectured that now we can say that the streamwise vortex control the large scale motion or vortex packet, and then they convert it to the straight by Richter effect, and then we have the same similar cycles. And then this branch actually recently predicted by the Delano and Jimenez and our groups, and then the new model stability theory actually predict that there is a possible growth of the streaky motions. So, and then this new model stability theory actually predict the quite good spanwise spacing of the streaky motions. So again, but there is no answer about the spin-wide length scale, but we are thinking about that this process may be related to the spin-wide length scale, but this is still in question. So, actually, as I said before, this new model stability theory actually predicted the large scale string amplification. So recently we actually confirmed this idea in the real turbulent flow. We conducted some sort of experiment. We put here roughness element in the upstream boundary layer, and then this roughness element actually generates the streamwise vortices. And then you see some sort of the streaky motion, which is converted from the streamwise vortices. And then when you do the time average, you can clearly see the well-defined streaky motions in here. So therefore, we confirm that this Richter effect indeed exists in the real turbulent boundary layer. So then, next question: then this whole process can exist or not? This is So this talk will try to answer partial answer to this question. So in order to examine this in order to answer to this question, we try to paint the small scale structure, and then we examine the existence of the self-sustaining process supported only at the outer scales. So now how do you paint this small scale structure? So at the first glance, it's important not allowed to have a backward spectral energy transfer from small to large. From this idea, we consider radial simulations with a static Smagorinsky model. This model is, as you know, purely diffusive. So we consider this kind of model, and here is a residual at the subgrid scale stress, and it's modeled in this way. Here is an eddy viscosity, boundary store damping function, and Smagorinsky constant, and the filter scale, and the normal velocity deformation factor. So, in order to gradually catch the energy from the smallest scale that we reserved, we gradually increase the Smagorinsky constant, from the reference CS, which mimics the spectra of the direct numerical simulations. So, with keeping this in mind, we consider radio dissimulation. These are the simulation parameter. We keep the mass flux constant, so the Reynolds number based on mass flux is the burst velocity is constant during the simulation. We consider a very large box in the streamwise direction, and then we put enough grid points to resolve the Newell cycle. So we do the reference simulation with the CS equal 0.05. And you know the CS equal 0.1 has been a commonly used value for the static Smagorinsky model. But and also this value actually showed the best result in prior tests. But the recent study by Hattori and Leather showed that the CS equal 0.05 actually provide the best posterior test results based on status. So therefore, we consider this value as the reference value. So you see that the present LDS actually showed a very good agreement with the DNS by the Jimenez. So we gradually increase the CS, and then you see that R tau doesn't change much. And here, in this case, you see this streaky motion, and their spacing is around 1.5 or 2. So you see also smooth scale motions. And we increase the CS, we gradually enter the smooth scale motions. Here you still have some smooth scale motion. Here, in this case, you see that you just have the long windering feature with a very long length. Here again we have the same feature, but I'd like to say this is a little bit over diffusive. So we just play with the disk field a little bit. So let's take a look at the disk field more carefully. And so we pick up the one streak, and then we put the side view. And what you can see is this streak actually inclined along the wall, and then with a 10 degree. And this is a streamwise elastic isosurface of streamwise elastic fluctuations. And then this figure actually was provided by Tim Nicholson here, several weeks ago. And then this is the rear turbulence boundary layer, and then see this is a result by the PIV measurement. And you see the same inclined angle. So this inclination actually related to this just only at the large scale dynamics. So now we take a look at the spectra to know what's going on in that. First, we take a look at the pre-multiplied spanwise spectra. And first, in this case, it's a CS equal 0.05, and this axis is lambda d over h, and this axis is y over h. I put here algebraic scale to emphasize the outer motions. Here you see the lambda d plus 100 peg corresponding to the Newell cycle, and then you see the outer peg at around lambda d equal 1.5 h. And to increase the CS, the structure around here was painted. Now you have nothing around there. So you have the peg around the logarithmic layer, and then this peg actually move along the lambda z to y. So that here this is not so clear, but it's true. And then in the case of CS equal 0.2, you just have this one wing number. And in this case, as I said before, the diffusion is a little bit too much. So you have a little bit, the spacing is a little bit moved, but they have the same feature like in this case. So now we take a look at the pre-multiplied streamwise elastic spectra. And here this axis again, the lambda x over h, and this axis is the y over h. So what you can see first, this is a typical length, the peak for the Newell motion. So here you have lambda x plus 1000. But when you go to out, you have another peak around the lambda x equal 3h, which has been considered as a signature of the large scale motions. And here you have long tail, and this long tail has been thought to be as the signature of the very long streaky motions. So we did the same thing, and we increased the CS. This peak actually is moved along the lambda x equal y. And here, again, in the case of the CS equal 0.2 and 0.3, you just have only long peak, the largest streamwise wave numbers in here. and then they are occupy the whole significantly in the mu region. But on the other hand, when you see that this outer region, hey, almost stay the constant value here, but it is a little bit more diffuse, so we have some significant, not so significant, a little bit more movements. But what you can see, the outer K doesn't move much. So, and as I said before, this one, actually this long streamwise mode penetrates into the wall, so that's why we observe that this kind of the URMS value doesn't scale with a simply R tau. We believe like that. And then this part is almost detached. There is no spectra around here. So also the existence for this structure, so they do not require the small scales. They just directly associate with these structures. So we can conclude that the two motions are very closely connected dynamically. So we did a box minimization like Jimenez and Moyen for this case, and to take a look at what's going on in here, and then we try to look at the simplistic dynamics embedded in here. So we found that minimal box to sustain the large scale motions was found to be this box size. So the box size, the smaller than this size, never sustain the turbulence. And then what you can also note that this side is a typical side of a large scale motion. And then this is the instantaneous snapshot. This red one is the isosurface of the cube, and then this blue one is some sort of the streamwise velocity fluctuation. Isosurface of streamwise velocity fluctuation. It is really bit mindering, and then so it is looking like traveling waves computed by the Hawking model. So we take a look at the time trace of the stream friction coefficient. So what you can see first, there is a big intermittency in here. Around the period is around the 100 or 150 in the non-dimensional time in outer unit. And then you see another period is around the 10 to 15 non-dimensional time in the outer unit. So here I visualize the status of at the time indicated by as a 1. Here, what you can see, again, this red part is a cube part, isosurface of the cube, and the blue part is the streaks, isosurface of the streamwise velocity fluctuation. So what you can see here, strong streamwise vortices. When you go up, when you go here, when you go to here, the vortices at the same level. I keep the same level in here. The vortices are completely almost disappeared, and then but on the other hand, this streaky motion was strongly enhanced. So this means that there is a Richter effect in this process. Here, we go to the 3, and when you take a look at 2 and 3, the streak begins mindering, and then the oscillation level become very large, becoming larger. So when you can see that this kind of vertical structure in here, aligned with this motion. Then when the CF reaches the maximum, the streaks completely break down, and the whole this process is very similar to the bursting phenomena in the Neumor cycles. So we think that now, so this large intermittent cycle seems to be a sort of the cycle of this process, and then this small streak, this small period is some sort of the. They are always observed that when CF reaches high, it seems to be the period of the streak oscillation at this stage. So this is a conclusion. We made 2 questions here. Can large scale self-sustain without small scale motion? And yes, it can. And then what is the self-sustaining process of the large scale? But I'm not denying these hairpin mergers, but this can be another possible scenario. So it seems to be strict vortices cycle similar to the Doppler cycle. Thank you. Thank you.
Was the first one. What do you say breakdown? What constitutes a breakdown?
You mean this?
What happens afterwards?
Afterwards, actually they are becoming some more or less something like that, and so something like that actually. So this stage is almost similar to this side, and the streaks are actually because of transient growth, you know, they need to their amplitude becomes decay.
These are low speeds.
Yeah.
So why, you know, in that first one,
Yes.
basically you have, so I assume that predominantly you have fast moving fluid.
Yes.
Where that corresponds to the minimum in speed friction.
Yes.
One, right?
Yeah.
And then, I don't know, sometimes it seems quite fun. Fast moving fluid to the highest speed. These are fluctuate.
Yes, pretty much a lot of fluctuations.
What is low speed friction?
And normally the friction is enhanced when you have a lot of the superstructure. Yeah.
Well, this is not that good, but it's not that good.
Okay. So,
Well, that's a minimal cut. So what's the bottom line? What's the CF?
What's the sorry?
I'm trying to understand. The CF, the bottom wall is the wall.
Yeah, here, you know, so you just see this kind of like the chain, and then these vertical structures are normally detected, so you don't see the vertical structure in the wall in this case. So you just only see the space.
Yeah, this regeneration mechanism quite
Yeah.
consistent with this,
Yeah.
but clearly explained in Schopper's paper in 2002. Right?
Yeah, of course. I believe so. So
So that must be.
sorry for that.
So enigmatic. It is clearly explained.
Yeah, the reason that I didn't mention this because here we don't know, but you said a strict transient growth, and I believe it can be like that for this process. So yeah, you're right.
We can have a dialogue on it. This is not it.
Yeah. So I
When you varied the Smagrinski constant, then the rate tau was changing. So do you have an explanation for the minimum value for 0.1?
Yeah. So here, so this is like we say that it's here is fully irregular. So we, as I showed before, here we catch the newer cycle, buffer layer cycle. But as you know, buffer layer cycle actually put a lot of they generate a lot of stream friction, and they are sort of the newer streamlined vortices has been thought to be as a generator of the stream friction. So you have you reach the lower state, but we increase the new T. So the mean is a little bit sharper. The mean velocity gradient a little bit sharper. So you get a little bit. You had this increase of the our tau, but in the case of CS equal 0.4, we don't have any. We fully consider this kind of perturbation. So our tau again, become lower because we don't have any structures.
Yes.
Did you look at the mean therapy profile? Since you changed
Okay.
right?
I prepared that. Okay, this is the velocity capsules. So here you see the agreement. Okay, but here you have a big difference because we gradually transferred from here. Okay, relatively linear. But here is okay. So here, this is a velocity fluctuation. Here, but as I said, the CS equal 0.3 is a little bit over diffusive. But this region shows reasonably good. And if I just compare the shape here by normalizing this value, it's okay.
Okay, very fast.
Yeah. Sometimes you said that this practice case that you have here was
Yeah.
where dynamically you give to the ones that you have away from the one.
Yeah.
And this is not part of reality. Why do you say that?
Okay.
The skills are quite different. So.
Yeah, you're right. So this is not clear to me for the moment, but so in the case of I try to compare with the buffer layer cycle. Buffer layer cycle, you have a peak around x plus 1,000 for the U spectrum. But when you do the box minimization, so the streamwise minimum length is around 400. And I believe that this is some sort of the primary instability wavelength. And then can be, this one is like, I believe that this one is a dominant windering length, and the windering would you like to make length, and this one is some sort of
I
length
don't
of
want to
string.
start the discussion, but I guess just kind of if you want to very fast jump.
Jay,
In the
I
meanwhile,
mentioned if you suppress the motion of 6, you get a layer, the one near the wall will appear for 6 times. No, but if you increase the CX and you suppress the outer motion, so also the motion near the wall with the outer state disappears for the same CX.
Yeah.
Maybe because that was different that way.
They are connected. We don't know.
Yeah, we don't know that, but I would like to say they are in track through the cycle. Yeah, this is certainly true. Yeah. But the string, the bodies, even if bodies are shorter than we have a long string. Yeah, as you said, Yeah. So.
let me proceed. Okay, so the TEPTO is testing opportunity stretching diagnostic for turbulent flows, and will be given by the sandham.
Right, so for light relief, pictures maybe. This is work with Johan Olsen here at KTH. It's sort of a double act. So I'm going to talk about the importance of autistic stretching and this criteria we've been looking at, and I'll show some applications to channel flow, and then Johan will come along and show some applications to his asymmetric diffuser. So, a quick outline of what I'm going to do. I'm going to start off with a bit of a digression into transition, where we're going to see the importance of autistic stretching in two examples. The first example is a brain instability in a transitional separation bubble and airflow. And the second example is a fairly classical example of autistic stretching in end-stage transition. So right after the primary and secondary instabilities and then the final breakdown into turbulence. And then I'll talk about the bit of channel flow, and this will set up Johan talking about the more complicated case that we've been looking at. So I'm going to start out with airflow flow, and what we've been doing over the last few years are direct numerical simulations of transitional separation bubbles on airflows. So here is an airflow, which is showing vorticity contours, and we have separation here. And if we look at the flow in 2 dimensions, what we have is vortex shedding from the rear of the separation bubble. That's a picture. I'll play it again, so you need to bear that in mind for what I'm going to explain in a minute. So the back of the bubble has this unsteady shedding of vorticity, and if you continue the calculation in 3 dimensions, and first of all you force it to transition to turbulence, and then you turn off the forcing, what you get is a full transition to turbulence, and we have a turbulent boundary layer developing under adverse pressure gradients at the back. But if you look carefully, you can see evidence of the vortex shedding from the back of the bubble still in the 3D case. The point about that was that the transition sustains even in the absence of upstream disturbances. So this is not a convective instability taking upstream disturbances from the free stream and amplifying them. This is some kind of absolute instability, or global instability. But if you look at the time average profiles, they're always absolutely stable. So there's no convective instability in the time average for this flow. So the question is, how does this instability sustain to keep us in a turbulent situation? So what we did was we took the 2D base flow from this example, an unsteady base flow satisfied with our Stokes equations, added small amplitude, 10 to the minus 10, random noise into it, and then ran the simulation in 3 dimensions to see how the small amplitude random noise grows. And what you see is that there is a very rapid growth of perturbations in span-wise velocity. It's exponential in time, and it all happens far too rapidly to be associated with an acoustic feedback loop. So it doesn't depend on disturbances getting to the trailing edge, generating sound waves, and then setting up a big feedback loop. So this is something inherent to the separation bubbles that's giving us a very rapid breakdown of 3D disturbances. Okay, and the mechanism for this comes in 2 bits. The first bit is upstream convection. So if we want something that's an absolute instability, we need upstream convection. This is showing you passive scalar being released into the flow. This is one of these big separating vortices. And passive scalar is clearly being fed back upstream. And you can actually see how it gets divided at the saddle points in between successive roller vortices. So in the unsteady flow, we have a mechanism for upstream propagation of disturbances. The other bit that we need to make this work as a transition mechanism is exponential growth. So this comes from an instability in the braid region. And in the braid region, terminology comes from mixing layers. We have the saddle point in between successive rollers. This is a region of high strain. So anything in this region is being strained out in this direction. And in particular, if you look at vorticity, that's aligned in that direction, and you write down the vorticity transport equation, you have that the rate of change of vorticity following fluid element is the vorticity multiplied by the strain rate. So you have a possibility for exponential growth of vorticity in these regions. Okay. And so these are contours of streamwise vorticity, and what happens is that vorticity in the saddle point region here grows exponentially. It also propagates into the vortex core. And you can see here it's starting to get advected back upstream. So we've got two elements for afterwards instability. We've got strong exponential growth in these regions, and we've got upstream propagation during the unsteady cycle. So disturbances can propagate upstream. And this maintains the transition process even in the absence of upstream disturbances. Okay, so that's one example of vorticity stretching in action. Here's an old example. This is from the first simulations that went through the complete transition process, starting with Tollman-Schlichting waves. So this is channel flow, Poisson flow transition. We start with TS waves, and then you add in a pair of oblique waves with equal and opposite sign. And this gives you secondary instability, which gives you lambda vortices. These then get elongated in the streamwise direction. And at this point, you pick up a mechanism that was first explained by Stewart back in 1965, when you have streamwise, near streamwise vortices lifting up low speed fluid. That's what we all recognize as a low speed streak. But in the region just above the low speed streak, you've got spanwise vorticity from the main shear layer, and you've got strained WDZ across this region, and that gives you a growth of spanwise vorticity. So you get intensification of shear layers here, and on the sides where the high momentum fluid is forced towards the wall, you get another region of growth due to vorticity stretching. Okay, then this generates a detached shear layer, which occurs in the spanwise symmetry plane of this calculation. This shear layer is unstable and will roll up to give you vortical structures. So this is a schematic of what was observed to happen in the simulation. And the lead vortex in this calculation was a very nice hairpin structure we really see during transition. If you follow that through to turbulence, it's a big mess. And you predict at that point. So that's two examples of vorticity stretching in action during transition. And in both of those cases, what we had were these diagonal terms in the vorticity transport equation being highly active. So in the first example, we had streamwise vorticity being amplified by this UDF strain. In the second example, we had spanwise vorticity being amplified strongly by this term. So if all the other terms are missing, then these diagonal terms will give you very rapid growth of vorticity and could be critical points in a turbulent flow. So really the idea of this project was to take a quick look at these terms and see if we have any special behavior in turbulent flow. So we looked at a measure which is basically the maximum diagonal element. So we take the absolute value of the vorticity. There's no summation on Greek indices, so the alpha is taken over 1, 2, 3, but not summed. So we take the absolute value of the vorticity multiplied by the strain diagonal component, and we just take the maximum value, which gives us a scalar quantity that we can look at in the numerical simulations. So, promised some movies. So, I'm going to explain what you're looking at. The blue is velocity. So, it's velocity equal to 10 typically in channel flow. And this is showing you the low speed streak regions, basically very near wall structures. The red is this vorticity stretching marker. And you'll see how that works when we look at the movie. These are the bits you see in this animation are basically located within the high speed streak regions. The yellow is VDU dy, which is going to show you lift up of fluid, and the green is low pressure, which marks where big events are happening within the flow, so very low pressure. And it's all happening very quickly. We don't see any very regular repeating patterns of large structures. The red, you can see, is mostly located within the high-speed regions. The yellow is the lift up, and that happens above low-speed streaks, and nothing's new here. And the green, you occasionally see these very big structures that are followed by a breakdown to small scales. And one thing that was noticeable in these pictures, perhaps I'll show that one again, there's a breakdown to small scales in patches. So this seems to be the bursting effect, where you get a big low pressure minimum sets off a process where you then get a breakdown to a patch of small scale turbulence, and that's a little bit clearer in a top view. So you occasionally get these patches of but everything is very irregular. So, oops. Right, so let's just summarize what we see in the pictures. The lift up measure, VDU dy, correlates with the tops of low speed streaks. The VDU and the low pressure regions are often next to each other. That's where a strong vortex generates lift up. We've got this intermittent breakdown to small scales, often following a large pressure minimum, which is the bursting process. And then the red in this animation was mostly following the high-speed regions. So what we have here is strong vorticity stretching in where fluid is going towards the wall. We have strong dWdz, strain in this finalized direction, and that's creating the high span-wise vorticity that then diffuses to the wall and gives you a drag on the surface. Some activity is also visible above low-speed streaks, which I'll mention in a minute, but just to see if what we've got is actually significant, we've looked at some statistics from these simulations. So there's two curves plotted here. The top one is basically the measure that we're getting. We're thinking in terms of entropy production. So this is vorticity squared times the maximum values of the strain divided by the minimum value. So this is the negative contributions at the bottom, positive contributions at the top. And if they were equal, you would get 1 coming out of the ratio. In fact, the ratio is 2 to 2.5 in the very near wall region, dropping to 1.5 in the centre of the channel. So that's indicating that the positive strain regions are more significant than the negative regions, supporting the fact that we do have a growth of vorticity in those parts of the flow. And the other property that's shown here is the entropy production contribution from the diagonal elements in the transport equation divided by the total. And you can see that peaks very close to 1 in the near wall region, which shows that this term that we've been looking at is perhaps the dominant term is very close to the wall. Some similarities that have not really worked out in detail yet with Ashurst, where he found preferential alignment of vorticity with an intermediate eigenvector of the strain rate. So this alignment of vorticity is perhaps what we're seeing in these results. What we saw was just events very close to the wall in the high-speed streak regions. If you multiply quantity by y, what you emphasize are structures that are away from the wall. And in this case, we can pick up clearly these inclined regions of high vorticity stretching, typically next to strong vortical motions. So in this case, this is secondary variant and clearly with low pressure as well. Secondary variant is in white, the low pressure is in green. And that's clearly having a lift up next to it, which is generating a large amount of vorticity stretching next to it. And so we have some sort of link in the dynamics of turbulence with this measure. So we're not measuring vortices, we're not measuring vortex sheets that are created by vortices, we're measuring somehow the dynamics that causes the vortex to generate a vortex sheet. So it's where something is happening in the turbulent flow. So I shall conclude. We've looked at this scalar measure of vorticity stretching. Some statistical support that this is something interesting to look at in the channel flow. It's, the positive values are more important than negative values, and there's large contribution to the entropy production. It mainly, if you just look at the quantity by itself, it mainly locates strained regions in the high-speed streaks, so it's the drag creation process in the turbulent flow. If you weight it with y, then you can look at formation of shear layers above the low-speed streaks and alongside low-speed pressure regions, and it serves as some kind of intermediate role in the dynamics between the worms, the low-pressure regions, moving the fluid around, and the creation of new vorticity and new vortex sheets that can then undergo instability to create new pressure and vorticity structures. What we're missing, I think, is the connection from the sheets back to lamp 2 via inflectional instabilities of the sheets. I think of a good measure for a developing inflectional instability in the vortex sheet. Okay,
thank you. So there's time for a few questions. Anybody?
Starting inflection is after it forms the ribbon. There's the stretching technique for that. Different mechanisms. The sheet.
You do see roll-ups of sheets, and it's usually
No, but in this case, it's not.
They're not really long enough to see multiple wavelengths. In transition,
you referred to the paper from Bill Usher and Alan Kirsten. But if I am not wrong, they did that for a shear layer, not for a channel flow. So do you expect? I mean, it was
turbulence, but there may be more than one paper.
Oh well, that's possible. But
it was isotropic turbulence for one, right?
Yeah, what I remember, it was a shear layer which they had, well, two flows of different speed, and they could analyze this alignment.
I know Asher's did there.
Do you expect? I mean, do you expect that it is reasonable to have the same alignment in turbulent flow as in a shear layer?
Yeah, I'm expecting similar processes to be going on, particularly at the smaller scales. Quantitatively, it's probably different. Expecting the same physics to be through.
Shall we move on to the next thing? Okay, there's another question.
In the first part of your talk, there is some criteria there that obviously we have to explain what we have to do.
You have to have backflow. Yeah, you have to have backflow of more than about 15% for it to be absolutely unstable. This is not true, no, it's only about 5%. That's a steady flow criteria, which is incorrect. But there's an unsteady phenomenon that's going to give you transition
Your base flow is not the distribution.
Well, what we did
When you say that it's not absolute, an averaging time. No?
Nur wenn es
sowohl
And what you're saying is that the stretching is not very stability. The stretching phenomenon, at some point, there is.
It's a secondary aspect.
So, we move on to the next tool. Dynamics in the turbulent three-dimensional solid flow by Johann Olson.
Kannst du mir die eine geben? Ja, das soll stehen bleiben. Ja, aber ich will auch mal vielleicht dazu kommen, fast alle zu benutzen. Ja, dann gilt die Formel dafür.